histograms. In essence, what we're looking at is a history of variation. If you recall, we talked about this issue of variation early on and said it's going to be one of the predominant issues across everything we look at. Nothing is exactly the same as something else. There's always variation. So what we're doing is we're monitoring or looking at and analyzing the variation that happens within a process. It creates a bar graph to provide a picture of the amount of variation in the process. Remember, graphs are pictures. We're also going to fit a line to this to get what's called a distribution curve, but we'll deal with that in a minute. The histogram is similar to a Pareto, but different, where the Pareto shows defects and defectives. Remember that x-axis was different defect categories or defectives categories, and the histogram at x-axis is actual measurements, or what we're going to talk about as bins in a minute. So again, they're similar in design, but one is defects and one is measures. So what I've got is I've got a fictitious part, the accountant's favorite term, widget. So I have specifications for this widget. And it is supposed to be 925 thousandths of an inch, let's just assume it's a length, plus or minus 20 thousandths. So in essence, what the designer has said is, this is my target. I'd like these at 925 thousandths of an inch long. However, as long as it's not 20 thousandths over that or 20 thousandths under that, I can work with it. I have a sample of 125 units. So in essence, I've captured this, and I have 125 measurements. Now, as I look at this, again, the labeling, remember, I can clearly see that the precision of this is to the nearest thousandth of an inch. When I run the numbers, then I see, all right, well, the largest one they made was 930 thousandths, and the smallest one we made, or the smallest one, was 910 thousandths. So when I subtract the low measurement from the high, or the small from the large, I have a difference of 20 thousandths, and that tells me that within the 125 samples, they varied by 20 thousandths. The total variation in there was 20 thousandths of an inch. All right, so now what I have to do is figure out how am I going to put these in bars. And I'm certainly not going to put them every thousandth of an inch. That just doesn't make any sense. So what we have to do is create or calculate what's called a class interval. All right, and the way we do that is the formula for class interval is the class interval is equal to the range divided by the number of classes or bins that I'm going to use. I go to a chart, and you've got one of these on the Blackboard site for you, and it tells me number of samples and number of classes, and it gives me a range. So if I have 50 or fewer samples, I'm probably going to use 5 to 7 classes. And remember, classes is synonymous with bins. Or if you think about it, if I said I'm going to have 7, that means there's going to be 7 bars on the chart. Each bar is going to represent a bin or set of values. 51 to 99, 8 to 10, 100 to 250, 10 to 15, 250 and up, 15 to 20. This is a guideline or rule of thumb for how many classes you're going to have or bins. So what I need to do is pick a number out of here. Well, I have 125, and I kind of looked at this and said, 11. And I think I broke it down by 25s, and 11 seemed to be a good number. It's you pick one that's in the ballpark. So I said, I'm going to go for 11 bins, or in essence, I'm going to ideally shoot to have 11 bars on my chart, 11 groups of measurements. So I'm going to calculate the class interval now. So I'm going to take the range, which is 20 thousandths, divide it by my 11 classes, and lo and behold, what I get is 0.001818. It's a repeater. But what I have to do, and remember we've talked about this before, is I absolutely must work to the precision of my spec. And the precision is nearest thousandth. Therefore, this value is going to be rounded to 2 thousandths of an inch. That is my class interval. Each bin will represent 2 thousandths of an inch. So now I have to set up the bins or set up the boundaries. In doing that, I start with my low value, the 910. And one of the things the inclination is to say, well, let's add 2 thousandths to it and make it 910 to 920. 12. Wrong. All right? There would be what? In that bin, there would then be what? 3,000s covered. All right? I want it to cover 2,000. So 910 and 911 represents 2,000. So that first bin is going to be 910 to 911. Those two values. Any one I've got that's either 910 or 911 goes into that bin. The next bin is going to be 912 to 913. Any value that's 912 or value that's 913 is going to go into that bin. The bins must not overlap. Hold them to the precision. And I didn't run all this way out, but when I get out to the end, bin 10 and 11, bin 10 was 928 to 929, and the bin 11 was 930 to 931. Now, I want to caution you right here. It doesn't always come out exact. It all depends upon how this guy up here got rounded. I'm shooting for 11. There's a very good possibility I might have wound up with 10, or I might have wound up with 12. Not a big deal. I don't want to be too far off my target of 11. If I'm one under or one over, I'm probably okay. Just many times it comes out to exactly what you're looking for, but simply because of the rounding, because you see, actually what I did is I added 200 thousandths to this number. So because of that, it's very possible I might have hit 930 before I got to the 11th bin. If that happens, don't worry about it, all right? Just keep in mind that we're shooting for 11. Hopefully we get there. And in this case, we did. We actually went one over the top, but that group said that. So now I'm going to show my measurements, or my bins, along the x-axis. And I'm going to show that the first one was the 910 to 911 and on down the line. I don't have 11 bars here, but so I know what each one is. And this is how many I had in that range. Here's how many I had in that bin. Here's how many I had in that bin. And I create a bar chart, all right? Running the measurements from low to high. All right, so this gives me a picture of the variation that resides within the process. Now, what I will commonly do with this is I will fit a line to it. Best fit on a line. And that's called a distribution curve. In essence, it shows how the variation distributes. And actually, you can see how it distributes around the mean here. So if I see this bell-shaped curve, what I'm going to do is I'm going to call that a normal distribution curve. Now, here's what that means. Here's the analysis. What that means is that the variation in these widgets comes from the process, not from anything else. In other words, there's not some mistake happening. There's not a bad piece of material in there. There's not a piece of equipment that's malfunctioning. There's not a person who's skipping a step or something. In essence, all the variation we have comes from the way we've decided to execute the process that makes these widgets. If I'm not happy with that, all right, then I can't find any one thing to pick on. What I've got to do is I've got to modify the process to try and tighten or alter the picture. So this is often a normal curve, and what it reflects is what we call common variation. Common meaning it is common to the process. All the variation in these guys comes from the way we make them. All right, there are some other options you might see in these charts. I'm just going to draw a couple small ones here. All right, what I have now is two skewed curves. Skewed right means that it tapers off to the right. Skewed left means it tapers off to the left. All right, this is a problem. Now, and remember, these are textbook pictures. These guys will not be exact like that. They won't just abruptly stop here. You may have a few odds and ends. You might see this thing then sharply come down or something. But what we're seeing here is what's called assignable variation. That means, fundamentally, that there is something in the process that's not being done correctly. Maybe a piece of equipment is past its maintenance point. In other words, there should have been maintenance done on it, maybe it should have been lubricated or cleaned and it didn't get done, and it's starting to create problematic issues. Maybe somebody, it's a 10-step process, and somebody says, oh, you know, I know a way that we can skip steps 5 and 6 and speed this whole thing up, and by doing that, it created a problem. Maybe I've got a load of bad materials. Maybe I have some materials I'm using that didn't meet my specification. What it means is that there's something wrong out there. It's not the process, it's something specific within the process, and we should be able to go out and find what's happening in a way that wasn't supposed to happen. In other words, if I've got materials that aren't meeting specification, I should be able to find them. It tells me I'm looking for something. That's when you put your detective's hat on and you get out there and say, okay, what's happening? Because you will find something. You know, where with the normal curve, you won't find anything. Everybody will be doing exactly what they said they'd do with the equipment you planned and the processes. But here, something's wrong. Now, one thing I like to comment about these is if these are not attended to, these curves are going to move. And I can tell you exactly which way they're going to move. This guy is going to move this way, and this guy is going to move this way, and pretty soon we are going to make, remember it goes from the small measurements to the large, pretty soon we're going to make a whole boatload of widgets that are undersized or a whole boatload that are oversized. And how do I know they'll move? Think about the brakes in your car. You look at the disc brake in your car, and it's got that little piece of metal that starts to squeal when the pads get low. When was the last time when that thing started to squeal, indicating the pads were low? If you didn't do anything, are the pads going to get better? No, it's going to get worse. Same situation here. If I don't attend to this, right now I may not be making any bad parts, but if I don't attend to it, pretty soon I will be. Okay? So it's a heads up, get out there and find out what's going wrong and fix it. The other pattern you might see, not too often, but it's worthwhile to at least know about it. Is what's called a bimodal. Bimodal pattern. Typically what this references is a screw up in the data collection. Remember, if I'm making widgets, and let's say I have 2 production lines that make the same widget, I want to collect data from each but not combine them. I have to look at each production line separately. What this would imply is somewhere along the line I collected data from production line A and production line B, though they're making both the same thing, and put it together. And one of these curves probably represents one production line and one represents the other, but I should not put them together in a chart. I should separate them into 2 separate charts. So if you see bimodal, it usually is indicative of the fact that you've screwed up on data collection somehow. You know, maybe I've got materials that come from 2 different suppliers. I want to evaluate those separately. And if I make my evaluation of the process using supplier A, and another process using the parts from supplier B, if those 2 data got mixed, then I'm going to probably have a bimodal curve. In other words, I want to evaluate the process that uses the stuff from A and then the stuff from B and do that separately. Histograms.